Welcome to section 7.7. Now we're going to discuss springs. And when we're talking about springs, we need to be careful about deciding, are we talking about the work done on a spring or the work done by a spring? Because one way or the other, it'll change the sign, positive work, negative work, that kind of thing. So looking first at the work done on a spring, whenever a spring is compressed or stretched, the work is done on the spring by some applied force, right? Now imagine if you're stretching the spring, the force and the displacement are in the same direction. So if we're looking at FD cosine theta, right, the dot product F dot D, then in that case we're going to have positive work done, right? But when you have work done on a spring, if the spring obeys Hooke's law, F equals Kx, right? And so it's positive, F equals positive Kx. However, if the force is so that's the force, right? F equals Kx. So to find the work done, then we have to use calculus, right? And this is a Hookean spring, by the way. If a spring obeys Hooke's law, F equals Kx, then it's called a Hookean spring. If it doesn't obey Hooke's law, then it's a non-Hookean spring. So just be careful about that. And so in this case now we've got F equals Kx. So then the work done on the spring by some applied force is going to be this. Work is the integral, right? We're adding up all the little work that's done over some distance, right? So x initial to x final. Here's our starting point, here's our ending point. So it's like this is a graph of the force, and we're adding up all the little pieces of the force over time. But what's the function that tells us the force? I'm going to substitute in here kx. So this is kx, because this is now this function. It's in terms of x dx. So this means I'm looking for the antiderivative of this with respect to x, and then plugging in these things, right? So that ends up becoming 1/2 kx from xi, or 1/2 kx squared, to xi to xf. We substitute in, so it's 1/2 k xf squared minus xi squared. Notice it's just the difference of the potential energy of a spring, a Hookean spring, right, if we use kx. And so that's where that comes from, right? It all ties together. So now the work done by a spring, if you're stretching a spring, when you're stretching it, the displacement is in one direction, but the spring is pulling in the other direction. So F dot x, or F dot delta x, the force dot product with the displacement, is negative. And so then the spring is doing negative work, because the spring is pulling in the opposite direction that the displacement is going. Okay, so make sure you know what we're talking about, the work done by the spring or the work done on the spring. Okay, and so work is done by a spring as it attempts to restore its length back to the original length. So let's see, work done by the spring, we get the force of the spring is negative kx, and then all of this ends up being the same, right? Except that this is negative, means this is negative, this will be negative, and since I still have the negative in front, then the work done by the spring will be 1/2 k xi squared minus xf squared. Notice it's just the negative of that, of the one that we had before, right? And so as long as we have both of those forces there, energy is conserved, because the work done by the person is the same as the negative of the work done by the spring. All right, so here's an example. Work done on a spring and work done by a spring. We have a simple harmonic oscillator, spring constant 250 newtons per meter, is compressed 0.06 meters by an applied force. We want to know what is the magnitude of the applied force required to hold the spring in this compressed condition. Okay, so let's erase the board. Get ourselves some space here. This should be simple. This is just F equals Kx. It's a Hookean spring. And so it's 250 newtons per meter times 0.06 meters. And so I'm going to get 15 newtons as the force necessary to keep it in place there. Now I want to know how much work did the applied force do compressing the spring from equilibrium to 0.03 meters. All right, so let's take a look. If we use calculus, we're going from 0 meters to 0.03 meters. F is a function of x dx. So this is 0.03. And f of x is kx. K we know is 250. So 250 x dx. So this is going to end up being 125. That's not 125. 125 x squared from 0 to 0.03. I plug in the numbers and I get, this is 0.1125 joules. Now I want to know the work done by the applied force compressing the spring from 0.03 to 0.06 meters. By the way, we're compressing this now, so the force and the displacement are in the same direction, so we're expecting the work done by the applied force to be positive, and that's what we're getting here. That's a good thing. So now we're going from 0.03 to 0.06, f of x dx. So this looks the same as this, except that now our starting point and end points are different. So 0.03 to 0.06. This turns out to be 0.3375 joules. This is more than this. Same distance covered, right? But not the same area covered. Here, this is more work. Why? Because there's more force. It's already compressed, so you have to exert a greater force now. Greater force is going to result then in more work having to be done. Now the applied force is removed, and the spring now oscillates about the equilibrium position with an amplitude of 0.06 meters. D, how much work did the spring do to return the oscillator to the equilibrium position? All right, work done by the spring. So now we're looking at negative kx, right? Or the negative of this. So D is going to be going from 0.06 to 3, or to 0, right, from the maximum amplitude back to the equilibrium position. And it's going to be negative f of x dx. And so this is the negative of what we had up here. So negative 125 x squared from 0.06 to 0. And so now this is going to be negative 125. I plug in 0 squared minus 0.06 squared. And I'm going to end up with 0.45 joules. Okay, that's interesting. Why is this positive now? Well, it's positive because the spring is now in this case, is pushing in the same direction as the displacement. If this is the spring that was compressed, the force on the spring is this way. And the displacement is also that way because the spring is restoring it back to its equilibrium position. So I'm expecting positive work, and that is what I get. All right, and then it says, if the mass of the simple harmonic oscillator is 0.5 kilograms, what is the speed of the simple harmonic oscillator as it passes through the equilibrium position? Okay. This now is conservation of energy. So for conservation of energy, I know K equals 1/2 mv squared. This is the work done by the spring. And so if that's the work done, that's going to be equal to the change in kinetic energy. So this is going to be equal to 0.45 joules. So all I'm doing is multiplying by 2 and dividing by m, and we end up with 1.3 meters per second. Okay. Okay, example 2, work done by and on a spring. We have a Hookean spring. Hookean, again, that means it obeys Hooke's law, F equals kx. And we have the mass of the block. They're connected and placed on a frictionless horizontal surface. Force of 100 newtons must be applied to compress the spring to 0.05 meters. Okay, So here's the sketch, and here's the block. It's 0.25 meters, and it says calculate the spring constant. So we know F equals kx. We're looking for k. We know the force and we know the displacement, and so k is going to be F over x. The force here is 100 newtons, and the distance is 0.05 meters. This is the same as 1 over 20, so 20 times 100 is 2,000 newtons per meter, and you can see the units right there, newtons per meter. It's Hookean, so we know that it obeys this rule, and we can apply that. How much work, or B, how much work did the applied force do compressing the spring from equilibrium to 0.05 meters? Okay, again, we can do this using calculus. We could also do this using conservation of energy, right? At zero, at the equilibrium position, it has 0 elastic potential energy, and then it has elastic potential energy of 1/2 kx squared. But again, to get used to the calculus, what are we doing? We're starting at 0, we're going to 0.05 meters. Kx dx, this is our function that tells us the force. And so we're going to end up with 1/2 kx x initial squared. Let's just do kx squared from 0 to 0.05. So this is half of 2,000 times 0.05 squared, and then it would just be minus 0. This ends up being 25 joules. Okay, so then how much work did the spring force do to return the oscillator to the equilibrium position? So now you've let go, and now it's going back. Well, the force of the spring is this way, and the displacement is also this way. So they're both in the same direction. It's going to be positive, and it's going to be the same amount of work as this. So 25 joules, right? Just like what we saw before. And then we want to know when the applied force is removed, what is the speed of the mass as it passes through the equilibrium position? Again, we know this is conservation of energy, so 1/2 mv squared is equal to the work done to get it to that point, which is, these are all 2.5 joules. Couldn't read my own writing. And so this is going to be equals 2.5 joules. Plug in the mass here, which is 0.25, and we get that V is 4.5 meters per second. So here's the tricky thing. Not all springs obey Hooke's law. Not all springs have this rule. They follow F equals kx. Some have a different function, that the force is equal to something else times x, x squared, whatever it might be. So in example 3, we have an example of a non-Hookean spring. So if the restoring force is given by this function, F equals negative 200x squared. All right, let's write that down. What work is done by an applied force that stretched the spring from equilibrium to 4 centimeters? So going from 0 to 0.04 meters. All right, so we're doing an integral, and we're looking for the work done by the applied force. So we're going to go from 0 to 0.04. We're looking at F as a function of x, dx. Now what is our force here? What's our function? 0 to 0.04. It's negative 200 x squared dx. All right, so this ends up being, when I take the integral, right, the antiderivative of this, I've got to think backwards of taking the derivative. And so this ends up being negative 200 over 3 x cubed, 0 to 0.04. Right? This would be the derivative of this, so we've got to work backwards. So this ends up now becoming 0.00427 joules. Right? And why is the negative there? So this is the force. This is the force by the spring. Since we're looking at the applied force, this would be the force in the opposite direction. So we're going to get rid of the negative, and we're going to leave it positive. So that's the first part of springs.